here. And today we are going to be doing SDM and substructuring in ME-scope. So we'll be tackling a few of the more technical topics within ME-scope. Sean, it looks like we got you from FlowServe. Sure we'll have a few other people that'll be trickling in here. Why don't we? My name is Mark Richardson, and my dad, Mark Senior Richardson, if you'd like, is going to be doing the presentation. If you got questions, Sean, during the webinar, feel free to type them into the questions little dialog box on the right-hand side, and we'll get those questions answered for you. At the end of the presentation, we also are recording this, so we'll be posting this on our Vibrant Technology YouTube channel, and we'll send out a link to that as well, so you can jump in there and take a look at that if you have some additional questions. Looks like we got a few more jumping on here now. Dad, I'm going to hand it over to you, and you can go ahead and get started. Again, if you got questions, go ahead and type them into that little question dialog box on the right-hand side, and we'll get those answered for you at the end of the tail end of the webinar.
Okay, thanks, Mark. Welcome, those of you who are attending wherever you are in the world. I know it's probably late at night, maybe early in the morning for some of you. This is our monthly 1-hour webinar from Vibrant here in Denver, Colorado. And this topic is, as Mark mentioned, a little more advanced application of ME-scope and modal analysis. We're going to look at both what we call experimental modal analysis, or EMA mode shapes, and even more specifically a modal model, which represents the dynamics of a structure from its experimental mode shapes. And then we're also going to compare those results with finite element analysis mode shapes, or a modal model. And we're going to work through the use of SDM, which stands for Structural Dynamics Modification. If you're looking at the screen here, this is the beginning of a new technical paper that we will have available on our website. Let me just explain the background of this. One of my colleagues from way back in the 70s at Hewlett-Packard, and then in the 80s at a company called Structural Measurement Systems, his name is David Fermenti. He and I developed a lot of this original software together. We marketed it as SDM during the 80s as part of the structural, or the SMS, Structural Measurement System software. It's been a part of ME-scope ever since. Vibrant was started in 1991, so a lot of these algorithms have been around for a while, but SDM is a very useful tool for, as it says, become a practical tool for improving designs of mechanical systems. It provides a very quick and inexpensive approach to investigating the effects of design modifications to a structure, thus eliminating the need for costly prototype fabrication and testing. So that's the whole idea behind SDM. It uses a modal model as opposed to a finite element model, which is a different computer modeling of a structure. But we're going to compare the two because ME-scope has FEA capabilities, not as advanced or sophisticated as a Nastran code, but we can do very simple models in ME-scope, and we can compare those mode shapes with experimental data. So this technical paper here is actually, I've extracted it from a book chapter that we're preparing, Dave Fermenti and I, that's going to explain the SDM algorithm and its various applications. And there's actually 4 applications that are implemented in ME-scope. They all do things a little differently, but they all rely on the SDM algorithm. Those 4 applications are We're going to look at substructuring here today, uh, adding tuned absorbers, which is a different way of using the substructuring capability of SDM. Uh, tuned vibration absorbers are used in many mechanical applications to suppress vibration. Hopefully we'll get to that today and I'll show you how that works. But if not, we'll do another session on it in the future. The third application is what we call modal sensitivity. And the whole idea behind that is to use SDM to explore the sensitivity of modes to physical modifications to a structure. And in the example that we have here, we see the brick wall effect. In other words, you can add stiffness to a structure and it will increase the frequency of some of the modes. You have to know what the mode shapes look like and how the stiffener is being applied. But you can only stiffen a structure so much and move a resonance. And you run into a brick wall effect where the resonant frequency cannot be increased anymore, no matter how much stiffness you add. The fourth application, which again is a combined use of SDM, and we can use it with our FEA capabilities in ME scope, and that's called FAA Model Updating. Now this has become a very popular subject because there's a lot of FEA modeling going on in the mechanical engineering world today. Computer models are being used more and more to anticipate vibration issues in new designs, new car designs, new tractors, new washing machines, whatever it is. So the whole idea is when there's different results between your experimental or your test results of resonant vibration and the FEA predictions of resonant vibration, what do you do about that? So FAA model updating is a way that we can use SDM to explore changing physical properties in an FAA model so that they match up, so the modes, the frequencies of the resonances match up more closely with the real world. So these are all applications of SDM that, and we'll see how the advantage of this algorithm, it's very quick. So we can look at hundreds, perhaps thousands of what if situations. What if the stiffness is this much? What if the thickness of the plate is this much? What if I change density, material properties of the material in a structure? So there's a number of different things we can do with SDM because it's such a fast and efficient algorithm. Not going to go through the math today. This book chapter, which is going to come out, is being published by the Society of Experimental Mechanics. It's not ready yet. Maybe this year it'll be published and we'll have a whole chapter that includes all of the mathematics and these examples that I just discussed with you here. Today, let's start with this example number one, attaching a rib stiffener to a flat plate, aluminum plate. And then we're going to look at three different cases here. EMA, again, EMA is the experimental data versus the FAA modes of the plate without the rib. Then we're going to look at SDM versus the FAA modes of the plate with the rib attached. And finally, we're going to look at SDM versus EMA, or the experimental results of the plate with the rib attached. So we're going to look at these three different cases here today. And here's some photographs of the flat plate. It's an aluminum plate, normally 3/8 of an inch thick. Over here in this second figure is the rib stiffener, and it's not attached. You can see there's 5 cap screws there that were used to attach the rib to the plate. And then finally, here's a picture of the plate with the rib attached down the center line. Now this is a substructuring problem because, as we saw up here with SDM, SDM takes the modes of the unmodified structure plus FEA elements that model the modifications, and it solves the problem and comes up with a new set of mode shapes for the modified structure. So in this case, when we talk about substructuring, the modes of the unmodified structure are going to be the modes of the plate by itself and the rib by itself. And we're going to see that we actually use a combined use of both FEA and EMA to come up with that modal model. We call it a hybrid model. And then the modification is that we're going to model those 5 cap screws with linear stiffeners. And when I say linear, I'm getting beyond myself here. In Emiscope, when we model rib stiffeners, we model them as a linear spring element. Now, more advanced FEA would use perhaps nonlinear, but we're going to use 5 springs, one for each of these cap screws, physically located exactly where the cap screws exist between the plate and the rib, and we're going to model those cap screws with 6 degrees of freedom with each spring. So 3 translational, X, Y, and Z. We're going to basically constrain the rib to be attached to the plate in 3 directions, X, Y, and Z. Plus, we're going to constrain the rotation of the rib with respect to the plate. And we'll see when we look at the results that that's very critical in a situation like this, because those cap screws are not only exerting stiffness in the X, Y, and Z, they're keeping the rib from moving away from the plate, but the torsional stiffness, the twist of the plate at certain frequencies, there are modes where the plate wants to twist and the rib wants to twist. And so those cap screws are going to couple the twisting of the rib and the plate together. So we'll see that here when we go through. Now here's a picture of the rib and the plate in Emiscope, and you can see the 5 springs there. In Emiscope, we simply denote the spring with a line element, but it's a special FEA element in Emiscope that SDM will use to model those 5 cap screws. Let me just go ahead and show you some of the results here. I mean, the question will come up, well, how much stiffness do I add? Well, to start out, you simply make them really stiff. So we're going to put in a torsional stiffness of 1,000,000 pounds per inch, or here it is in newtons per millimeter, for the translational stiffness. So that's the XYZ, that's sticking the rib to the plate with the cap screws. And then the torsional stiffness, again, 1,000,000 inch-pounds, so it's a torque per degree of rotation. And again, we're just going to put in some very stiff values to model those 5 cap screws. Here are the impact test points that we use. Now this is something else. When you test structures, structure like this, very easy to test. We just put it on some foam rubber, actually just some, gee, what do we call it? Can we see it here in the picture? It's just a bubble wrap. You can see the bubble wrap underneath of the plate, and it's just laying on a table. So a little bit of a free, except, you know, there is some stiffness being added due to the bubble wrap. These are the impact points, 30 impact points. That's plenty of experimental data, but you'll notice that we didn't even impact the plate at the same points where the rib is attached with the screws. In other words, the screws are in between. So that's where we're able to take advantage of the FEA data. And down here, we're going to solve for FEA. Here's a description of the FEA model of the plate. And you can see these are what we call quad elements, FEA quad elements. We put in some physical properties for the plate or the Young's modulus. These are handbook values, density of the aluminum, Poisson's ratio, and the thickness of the plate. So not a lot of information to model such a simple structure like this. So we're going to solve for the modes of the plate, both FEA, and we're going to compare those with the experimental modes. And here's a MAC diagram, MAC being modal assurance criterion. This is a metric that measures the likeness of a pair of mode shapes. So here it is showing 14 mode shapes, and when the MAC values are between 0 and 1, when they're in the high 90% or 0.9 and above, here you can see the worst case is 97%, that first mode there. All the others are higher. That means that the experimental and the analytical mode shapes are matching up very well. So the first step of testing and modeling a structure like this, and this is just a plate without the rib, would be to impact it in a few places, get some mode shape components, and then compare like components, in other words, the same point number, the same direction, between FEA and experimental. But you can see that FEA, we're going to have a lot more degrees of freedom in our mode shapes because we've got more elements in here than we had test points. Here's where we tested it with the impact testing, only 30 points. This model here has the same points as the test points, but it has additional points in it. So there's a matchup of the analytical and experimental. And now, since we have a good match of mode shapes, we're going to use the FEA mode shapes because they have rotational degrees of freedom. And we need those in order to model the dynamics of the plate, so that when we attach the 6 degree of freedom springs between the plate and the rib, we can model that torsional stiffness correctly. Normally we don't ever measure that in an experimental situation. We only measure the translational or the XYZ motion of the plate, which we did here from tests. But since we got a good match between the translational degrees of freedom, we're going to create a hybrid modal model, which will consist of the following: the modal frequency and damping of the EMA modes, because those, and we'll see how we get those from curve fitting RF measurements, those are more accurate. Typically the FEA frequencies are not as close to the real world, and there is no damping in the FEA model. Too difficult to model, so we can get modal damping from experiment, whereas we don't get it from FEA. But we have the DOS, degrees of freedom, at locations where the EMA data may not have been acquired. So I mentioned that up here. The FEA model has degrees of freedom at the points where the springs are going to be added between the plate and the rib. You can see the springs are halfway between the experimental test points, but we have mode shape data from the FEA model at those points, so we can go ahead and use that in SDM to model the cap screws correctly and located in the correct direction. And so this is, again, this hybrid model. The mode shapes include rotational DOS, which typically are not included in an EMA, in the EMA mode shapes. And then this final thing, and I won't get into this, this is a mathematical issue, but in order to define the dynamics of the plate and the rib, we need to have mode shapes that are properly scaled. In other words, they need to preserve the mass, the inertia, the stiffness, and in this case the damping also of the actual structure if we want a realistic dynamic model of the structure. These mode shapes, when they come out of an FEA solver, and this again is the Emiscope solver, they're scaled to what we call UMM, or unit modal mass. Now that scaling preserves the dynamics of the structure in the mode shapes themselves. So I don't have a mass matrix, I don't have a stiffness matrix, especially when I take experimental data. But when I solve for the FEA mode shapes, they are scaled properly so that they are a correct dynamic model, and we call that a modal model. So it's a dynamic model of the structure represented by its modes only. Okay, so here's a comparison of our FEA and EMA frequencies, and of course we have EMA damping. We don't have any from the FEA model. And so this is just a numerical list of frequencies and Mach values. Well, we saw the Mach values in the Mach plot here. They're all matching up. These red bars are comparing an FEA mode to an EMA mode. You can see up here FEA mode shapes, EMA mode shapes. They're matching up very well. So this allows us to use the best data from both EMA and FEA to model this dynamics. Okay, the next thing we're going to do here is model the rib. A similar type of exercise here where we're going to build an FEA model of the rib just floating in space by itself, because the springs and the cap screws modeled by the springs are going to attach the rib to the plate. So we need the dynamics of the rib in free space, essentially, what we call free boundary conditions. Here are the FEA quads of the rib, and let me go down here and see what else we have. Okay, here's some experimental data for the rib. Again, we just impacted it at a few of the points on the rib, just laid it down on some bubble wrap and hit it with a hammer to get its free frequency and damping, the modes of the free or the frequency and damping of the free mode. So here's a curve fit. When we get into SDM or into Emiscope, we'll do some of this curve fitting, and you'll see how that works. Again, we build a hybrid rib model the same way as we did with the plate, and here's what it looks like. Now we don't have the Mach values shown here, but we have FEA frequencies. Now the first 6 frequencies are what we call rigid body modes. So the FEA solver will give us the 6 rigid body modes, 3 translational and 3 rotational mode shapes of the rib in free space without any boundary conditions. And so we need those mode shapes. That's part of the modal model for the rib in order to attach it correctly to the plate. Here are the frequencies that came out, but we want to use the experimental frequency and damping, the EMA frequency and damping that we got from impacting the plate and the curve fit right here. Here's some of the results. So we want to use those frequency and damping and apply those to these what we call flexible body mode shapes. So we have what, 7 through 16 are flexible mode shapes. The first 6 are rigid body mode shapes, and this is the modal model for the rib, the hybrid model that we're going to use with SDM to then model the attachment. So we have these 2 hybrid modal models, and we put them together in what we call a substructure mode shape or a substructure modal model. And in Emiscope, that merely amounts to copying the mode shapes of one of the structures, the substructures, in with the mode shapes of the other substructure. So we got two substructures here, the plate without the rib and then the rib. And when we paste those together or copy them together into the same shape table, what we've done here is to number the points on the rib with much higher numbers than the points on the plate. So the plate, you can see here's the test point numbers where we impacted it, and they go up to 30. You can't see them all here, but you can see some of them down the center line here numbered. Those are the impact points where we tested the plate. But remember, we also have FAA data in the hybrid model at the attachment points of the stiffeners. And then the rib modes are going to be numbered with higher numbers so that when we put these together in one substructure modal model, they get stored in a sort of a block diagonal. You have to picture this in your mind, a block diagonal format. Let me show you that when we get to Emiscope. So here's some SDM results. Let's go run Emiscope and take a look at some of this. So here we are. This is Emiscope open to this project. Let me show you what's in this project. Quite a bit of stuff. I've got 3 different models of the rib and the plate. Here's a plate and rib. This is the one we're looking at right now. Here's a copy of the plate and rib. We're going to use that to do some comparison animation. And then down here is a TA plate and rib. That's a tuned absorber. And we've added a model for the tuned absorber to the plate and rib model. Here's some data block data. This is really, here's the one that I've already talked about, the 30 plate FRFs. So we measured with an impact hammer the force and the acceleration response of the plate at 30 points. Here is we made only 24 measurements of the plate with the rib. So once the rib was attached, we couldn't really test down the center line. Well, we could, but the easiest thing is just to test the plate at the other points on the bottom plate where the rib, we're not testing down the center point, but these are enough points to be able to compare our experimental data with the SDM results. So that's what we did. Again, making our job as easy as possible when we want to compare or solve a substructuring problem like this. Not taking a lot of experimental data. Okay, well down here, these are some data blocks. Hopefully we'll get to that today, maybe not. We'll have to go ahead and this is some FRF synthesized from our modal model before the rib was attached and after. Not the rib, but the tuned absorber. Here's a bunch of shape tables. Shape table is just a couple of spreadsheets with the frequency and damping and the mode shapes in there, and we'll get to that. And then down here are some scripts. Now, Emiscope, a standard part of Emiscope, are what we call script windows. VSL is vibrant script language. Script language in Emiscope is simply a window followed by a command in that window. So all the commands in Emiscope can be added to a script. And when I create a script window, it also creates in Emiscope a hotkey. And you can see here are some flaming hotkeys up here. The first one is the EMA plate modes. And when I press that button, that hotkey is going to execute some Emiscope commands in a script window. And we'll see how this, once all this is set up, I can simply go through and press any one of these hotkeys, and Emiscope's going to do a whole bunch of things that I've already programmed into the script for that's being executed by that hotkey. Here's the next hotkey. It says FAA plate modes. So that one obviously is going to do a solution, an FAA solution in Emiscope to give me the plate modes. Here's a third hotkey that's going to assemble the substructure modes, what we just talked about, the block diagonal form of the plate modes and the rib modes. The rib modes being a free condition. Okay, here is a comparison then of SDM versus FAA modes. So now we're going to get into looking at how did SDM model this versus FAA solving the complete problem with the 6 degree of freedom springs between the plate and the rib. So that's the first thing we can do, is just compare SDM with FAA. Okay, here's SDM with the EMA modes. So this is the real proof of the pudding, so to speak. We went back and impact tested the plate with the rib, and this is going to be a comparison of SDM with the EMA modes, or the experimental results when the rib is attached. Finally, here's the tuned absorber. We talked a little bit about that, attaching a tuned absorber. Here's modal sensitivity. We talked a little bit about that. And finally, FAA model updating. So these are all hotkeys that will automatically take us through some Emiscope steps. And so we may go look at some of this, the scripting, but I'm going to start off by just pressing this EMA plate modes, and we'll see what happens here. Okay, so it's positioned a bunch of windows, and I can see some experimental FRF data here, and it's finally stopped and told me that what it did was it curve fit 30 FRFs to extract 14 modes of the plate. So this is experimental data, and I'm still running this script, but let's just take a look at the data. Here it's going to tell me press the continue in the lower left progress bar to resume. So I have to keep that in mind. And here's the continue button down here on the progress bar, and that's just the program. The script is just waiting for me to press it so that we can go on. But let's look at this curve fit here. Here's the 30 measurements. This is regular old curve fitting in Emiscope. This is using what we call a stability diagram. So we went through, and this is very nice clean data. You can see there's a little noise down at the low frequencies, and in some places where there isn't a resonance. But as I draw through here, this is the log magnitude of the data that was taken out to 900 hertz on the plate by itself without the rib, and we identified or extracted the properties of 14 modes. So here are the properties over here: the frequency, the damping in percent, and residues. Now, residue is the strength or the amplitude of each of the peaks in each measurement. So as I scroll quickly, you can, if you watch over here, the residues are changing because those are mode shape components. Those are showing us in each of these 30 measurements the components of the mode shape. And you can see that my DOFs, right here next to my scroll bar, you can see which DOF we're looking at here. The first one is the roving, and that's, well, here, let's just look at it right up here, 22Z. So we're looking at point 22 in the Z direction. That's vertical, and there's a reference of 5Z here. So as I scroll through, the 5Z is where the accelerometer was located, and I did a roving impact test at 30 points. simply impacted the aluminum plate at 30 test points. And this is the data, and this is the curve fit. Now let me just turn this cursor off here for a minute, and I'm going to go down here and zoom in because this is curve fitting, and I want to just look at these two closely coupled modes here. So let me scroll this so you can see there they are. There's the two resonance peaks, and we're zoomed in down here. Now this is a stability diagram, and as I scroll through here, you can see that the curve fitter went in and it solved with a model. We didn't tell it how many modes were there. We just said go curve fit this data and find the frequencies and damping in this model and stability. Maximum model size was 50. And we're using a curve fitter called AF polynomial. There's a number of curve fitters we could use in here, but this one was the one we used, and that was controlled from the script. When I push the hotkey, I can go back and do this as many times as I like, and it will just do this job over again. So what this did was to find some stable, and if I put my mouse over here, you can see that this is an estimate of the frequency and the damping of this particular resonance. And if I scroll all the way up here and I select these over here, it's already saved a value for each of these. Let me just put this down so you can see it. There is the average of all of those, what we call pole estimates, for these two modes. They're two closely spaced, not really tightly coupled, because we can see the two resonance peaks pretty easily there. So this is nice, easy data to curve fit. The red line up on the top is laying on top of the experimental data, and there's hardly any difference in the vicinity of each resonance. So that's what we want to see. In any good experimental data, we want the red line to lay on top of the experimental data, which is the black. Now, if I sometimes can curve fit and get the red line to lay on the data, that may not be good modal parameters over here in my list. So this is a necessary condition. If I have good modal parameters, the red line should lie on the data, but it's not sufficient. In other words, what I'm really looking for is some good modal parameters over here in my list of curve fit results. How do we know whether they're good? Well, you can compare them with FEA, which is what we're going to do here in this case. Compare the FAA mode shapes with the experimental mode shapes. And if the MAC values are close to 1, that's a confirmation that this curve fitting operation and the experimental data itself was reasonably accurate. Now, we can always have noise show up in our data, and this, of course, is very clean data because it was such a simple test setup, and the structure, the resonances show up very nicely in the data. So this is a stability diagram down here. This is one way to curve fit. The other way that we use often is what we call a quick fit. Quick fit we have to tell it how many modes are in the data, and with a quick fit we'd have to either count the peaks in this mode indicator function down here below and tell it how many modes are in there, and then quick fit would quick fit this data. In this case, we use the stability diagram to tell us where the modes were and give us some stable estimates of the frequency and damping. Then we went on, and the scripting went ahead and solved for the residues. That was all in the script for this particular hotkey that I pressed up here. So let's go on, and you can see that it's the scripting is still waiting for me, and I have to press this continue button down here. Now, if it waits too long, it's going to finish and then go on to the next step whether I like it or not. I'm going to press continue. Now it's moving on in its scripting, and now it's telling me animation will sweep through the EMA mode shapes and compare each with its maximum MAC ODS. Wow, that's a lot of words. What does that mean? Well, let's just look at the picture here. So we've got a comparison animation going on, and it's sweeping through the mode shapes. And this is a shape table here. And then here's my original data block over here with FRF data in it. And I've got a comparison animation going on here. Now, when I have a lightly damped structure like this, the curve fit results are going to very closely match the ODS results. So what I'm looking at over here when I put a cursor in this data, and you can see the cursor moving along over here automatically because the animation is matching up the frequency of the EMA mode shape that we got from curve fitting with the frequency of the cursor over here. And then the animation is displaying on the left. You can see up here, these are the EMA plate modes. Over here are the 30 plate FRFs. So for lightly damped data like this and nice clean measurements, you'll get this kind of result. And many times people don't even go through the curve fitting, just use the ODS, just put the cursor in the data, and at a resonance peak you're going to get a close approximation of the mode shape, because that mode at that frequency is dominating the ODS. In other words, the structure wants to vibrate very freely at that particular natural frequency. So you can see the mode shapes going by here, and that's because I've set the animation up to sweep through the mode shape window here, or the mode shape. This is what we call our shape table. So the frequencies are up here in this spreadsheet, the mode shapes are down here in this spreadsheet, and you can see there's just 30 what we call measurements. The M-pound number is the measurement number. There's 30 measurements animating this plate model for each of these cases. Let's move on. We're chewing up our whole hour here. I'm going to press the next hotkey, and that one says FAA plate modes. So now we're going to go through and actually solve for the FAA modes of this plate. Okay, it says 20 FAA modes will be calculated using 80 FAA quad plate elements. So here's a picture of the quad plate elements down here, and I have to dismiss this dialog box before it will continue, and it's going to go through, and Emiscope is just solved, and it solved that quickly. Now it's comparing the EMA and the FAA mode shape pairs with maximum MAC. So again, the animation, because I've said match up these mode shape pairs according to their maximum MAC value, this is an animation of, on the left is the EMA data, on the right is the FAA data. Now if I turn on points here, you can see that there are many more points on the FAA model than the EMA. We only got 30 points over here. We've got quite a few more points over here. Plus we have the rotational DOFs in these mode shapes. But the MAC value is simply comparing the like points and directions. So we can always do that, and that allows us to compare a more complex. Let me click up here. It's sweeping again. So 101.5 is compared with 91 down here. So the frequencies are different, but the mode shapes are very close to one another between FAA. All right, now I'm going to go, and this next button here is going to build the substructure modal model, or it's going to merge together the hybrid modes of the plate with the hybrid modes of the rib stiffener. So let me press this one. that was a quick look at the okay, it's opening up some windows so it can show me everything here. And here are 14 rib modes and 16 plate modes of the unmodified structure. These are going to be used by SDM to model the rib attached to the plate using 5 6-degree of freedom springs. So this is the, well, I gotta hide some of this stuff here. Well, let's get out of here. It says click on the select shape button to display a substructure mode. I got a couple extra windows up here. Okay, so here are the substructure modes. So there's the first one. That's just the first torsion of the plate. There's a bending of the plate. So we're going to walk through a number of these plate modes first. If I click down here on number 15, there is one of the rigid body or the free modes of the rib. There's another one. So there's going to be 6 of these. These came out of the FAA solver, and we've merged them together with the modes of the plate. So these are all the rib modes now we're looking at. Now I could sort these in frequency. SDM doesn't really care. It just needs the modal data, and it needs the frequencies and the damping of these hybrid modes. So these are all the modes of the rib. If I go back and click up here, these are the modes of the plate. So let's make this a little larger here, and I'm going to center this, and we'll just look at this block diagonal form of. You can see here that through shape 14, it's now scanning through these shapes and displaying them. But shape 14, up through shape 14, I have data in here, and now from shape 15 on, it's just a bunch of zeros. Unless I scroll down here to some point numbers that are on the rib. Remember, I showed you a picture of the rib point numbers are numbered much higher than the plate point numbers. Now I have data for the rib, and if I go back over here for the plate, for those lower frequencies, or the lower shape numbers, I have 0. So that's what we mean by the block diagonal format. And I need to have this model animate on the or this data animate on the models so that SDM will model everything correctly when it adds those springs between the plate and the rib. All right, let's go ahead and do that because we're running out of time here. SDM versus FAA. So now we're going to go right ahead and solve for the FAA shapes with the springs between the plate and rib, and the SDM shapes, and come up with a comparison of the two. Okay, so here are the FAA shapes. FAA modes calculated between the plate and rib using 110 FAA. So we went back and solved for the modes of the complete model with quad plates on the rib, quad plates on the plate, and the 5 6-degree freedom spring. So here are the, okay, so it says press continue to resume. That's this button down here in the corner. But if we want to just look at these modes of the plate, the FAA solver is going to give us 6 rigid body modes. So here they are. As I click through, you can see the plate and the rib. They're just moving together in space because that's how the FAA solver handled the complete FAA model. There is the first FAA plate mode at 96, and you can see. Let's go back and look at this. This is not a plate mode. This is the first mode of the structure, and both the plate and the rib are twisting together. Now here's the rib just riding on the plate on a uh, basically a fixed deformation of the plate. Here's another mode where the plate and the rib are twisting together. So that's what those 6 degrees of freedom springs are going to model for us, is the basically the torsional stiffness between the rib and the plate. There's another twisting mode of the rib and the plate combined. So let's just go on here and see what SDM comes up with now using a modal model. SDM modes will be calculated for the rib and the plate using 30 substructure modes and 5 6-degree freedom springs. So we looked at the substructure modes, and let's go on and let SDM solve for this case. So it's going to go through, and now we're looking at the comparison SDM versus FAA with the maximum MAC. So this is showing us the comparison between the two, but let's go back to this first one. SDM found the first mode at 108 Hertz. Down here it was 96. So we're off by about 10 Hertz again. But the mode shapes, if you look at the MAC value, is 100%. So SDM modeled that joint stiffness between the rib and the plate. It modeled the joint stiffness correctly using a modal model. The second mode, again, 99%. The frequencies are wrong, or let's say they differ quite a bit between experiment and analysis, but as we let this walk through these mode shapes, you can see that SDM and FAA are modeling the joint stiffness. Oh, here's another mode right here. Let's just stop and look at this one. I'll just leave it there. See that SDM modeled that combined twist of the plate and the rib. I'll click back here again. Correctly, in the sense that it compares very well with the FAA result. There's another mode where it's just bending of the plate and the rib's just going along for the ride. And what is this one? Oh, another bending or a twist, combined twist of the plate and the rib. Now we're starting to lose accuracy. These are only 91% alike. In other words, there's 95, and the accuracy of SDM versus FAA is starting to diverge. Now we have what looks like the same mode shape, but in fact the MAC values are very low. So this is what we call a truncated modal model. SDM has gotten about the first 10 modes out of the 30 that it worked with. The first 10 line up very well with FAA, but as we get to the higher frequencies here, we've got 30 modes. Let me scroll this a little bit further here, and we can see, okay, so we've got 30 modes in here, but as we get up higher in frequency, there isn't a good match between SDM and the FAA mode shapes. Okay, Mark, I'm going to wrap this up unless we have some questions.
No questions at this time. If
No
you have
questions.
some,
All
go
right,
ahead and
well,
type them in there.
we've just about finished our hour, and I'm going to have to promise those who wanted to see the tuned absorber example or the modal sensitivity or the FAA model updating, we're going to have to revisit those subjects in another monthly webinar. Now, let me just give a little quick advertisement for next month's webinar. We're going to do something completely different with Emiscope. We have developed a new database that essentially has unlimited storage capacity, an archival database for use with Emiscope, and we're going to show you how it works with walk-around data collection for monitoring machinery in a plant. This is a very popular use of Emiscope, where we can make a movie of the ODS of a machine from a very small amount of experimental data. We can compare the ODS of the machine. Let's say it's a pump and a compressor and a transmission. Last month's vibration versus this month's vibration. We can do it numerically. We can do it like we're doing here with mode shapes, but we can just do it with ODS data also. But we need an archival database. Typically, with walk-around data collectors, hundreds, maybe thousands of machines are monitored on a regular basis in a process plant. So we now have a database for Emiscope that can save that archival data for hundreds, thousands of machines, and then you can compare ODS data from 1 month to the next, or one set of measurements from the next, as a way of documenting the health, the vibration health of machinery. So that'll be quite a different application. We'll use hotkeys, we'll use scripting in Emiscope, we'll use the archival database, and show you some ODS results next month. Mark, I'm ready to wrap it up. Anything else?
That'll do it.
All right. Well, thank you for your attendance, and we'll see you next month if you're interested in walk-around data collection. And then we'll schedule another session maybe in 2 months for looking at this case here of the rib and the plate, and looking at modal sensitivity and FAA model updating. So thank you for your attendance. We'll see you again.